Welcome to part 1 of the module on patterns and frameworks for service configuration and activation. In this part of the module, we'll begin by describing the component configurator pattern. To motivate this pattern, let's talk about enabling and enhancing server configurability and reconfigurability. The context for this is that some implementations of web server components depend on either static or dynamic factors. Some of the static factors include things like the number of CPUs or cores available when you start to run. Other factors include the version of the operating system that you may be using, which may have certain enhancements or certain optimizations enabled. More dynamic factors include things like what the network load is and the workload that's being sent by clients. So what are the problems? Well, if you prematurely commit yourself to particular implementations of the components in the web server, this can be either inflexible or inefficient because there's certain optimizations and design decisions you really can't make without having knowledge of what takes place as you begin to launch or run your application. Moreover, if you fall into the tendency of trying to group everything together into one big module to have all the different alternatives covered, you can end up with bloatware, which is very large and very slow because it won't fit into caches and you're including a lot of capability that really isn't needed. So what can we do to address these issues? Well, as we'll describe here, we're going to apply the component configurator pattern in order to assemble the desired web server components more dynamically, late in the design cycle, either at installation time or even at runtime. The component configurator pattern decouples component interfaces from their implementations and makes it possible to dynamically configure or reconfigure these implementations at various points of time in the life cycle. And you can even do this in a way that doesn't require having to shut down and restart running applications. The diagram on this slide illustrates the overall structure of this pattern. Some portions are infrastructural. There's typically some kind of class interface or messaging interface that you inherit or implement that provides you with lifecycle operations, things for initializing, finalizing, suspending, resuming, and so on, the components that are being controlled under this pattern. There's also a way of being able to store a group of dynamically and or statically configured components into some kind of repository, so you actually know what constitutes the space of different implementations available at any given point in time. Yet another piece of the structure of the solution is some kind of component configurator that orchestrates the way in which various components are dynamically brought in, dynamically removed, suspended and resumed, and so on. What you typically do then is you go ahead and you inherit or implement these various hook methods to fill in concrete components that will be used and managed in terms of their life cycle by these more abstract elements. If you take a look at this URL, you'll find a paper that talks in more detail about the component configurator pattern. So let's also talk a bit more about the dynamics of this pattern. This set of slides illustrates the various ways in which either an application or an administrator can interact with the capabilities defined by the pattern in order to configure the system and assemble it more dynamically and more flexibly. So typically, under some directive from some place, be it an administrator or an application, the component configurator is instructed to configure a service or a component into the address space of the application process. That will then go ahead and look into some kind of dynamic link library or shared object, pull out the various information, typically in the form of a factory function, that will create the appropriate instance of the component with its appropriate implementation. That will then get stored in the component repository, and the service can then begin to run to do whatever it is it needs to do. Some examples of capabilities that work like this historically have been things like loadable device drivers for protocols, things like transport protocols or device drivers on various kinds of operating systems. Java applets have historically worked this way, as well as the ability to load components into application servers dynamically based on some type of script that's read when they start up. We can apply the component configurator pattern to JAWS in a number of ways. First, what we can do is we can implement a bunch of different threading models for our particular web server, some that will use thread per connection, thread pool, various kinds of asynchronous processing with threads, even more conventional reactive approaches. And we can have these different implementations available and stored in various DLLs or shared libraries. And then these shared libraries and DLLs can be used to link in the appropriate implementation that's desired under the appropriate circumstance in which we find ourselves when we begin to run our program. Key to note that by doing this, the implementation only has to pay the cost in terms of memory footprint utilization for the services that it actually uses at any given point in time. And moreover, we can change these services over time as well. So this leads us into a discussion of some of the benefits of using the component configurator pattern. Chief among these benefits is this concept of parsimony. You're only paying the cost in terms of memory footprint and utilization of the actual components that you need. The ones that you don't need don't have to be linked in. You can also centralize the administration, so all the components can be configured in a uniform, common way with a uniform API that's used to initialize them and finalize them and so on. Because you're building your components out of smaller pieces and your applications are scripted out of building blocks, it enables a much more modular approach to building your software. And by doing things like this, you also encourage the use of various kinds of unit testing, test-driven development, continuous integration, where you can assemble the different parts and test them in isolation, and then integrate them together dynamically to see how they work. The last main benefit of Component Configurator is indeed this concept of dynamic configuration. You can wait until late in the design cycle to bring in just the elements you need, just when you need them, and tune them to the particular details of the context or environment in which they run. There are, of course, some limitations associated with all this flexibility. One of the chief limitations is the fact that by bringing together an application whose components are dictated dynamically, you end up limiting or reducing the amount of determinism. It's not always clear what is actually being linked together and whether those things are correctly ordered, whether they'll be brought in at the right time, whether they have access to each other in an appropriate way. So that makes it a little bit harder to know just exactly what your system does. Another consequence of this as well is there are certainly robustness and reliability issues. Some things might work fine in isolation, but when brought together might have conflicts. This is particularly true with respect to properties like timing properties, where things may run fine in isolation, but when you combine them together dynamically, all of a sudden their timing properties begin to vary. Naturally, there are also some security implications. You have to be careful you aren't loading Trojan horses into your address space without really knowing what they're going to be doing. Another issue is when you start using shared libraries or DLLs, some implementations, especially ones that use so-called position-independent code to allow the modules to be linked in various parts of memory, those can incur some extra levels of overhead for indirection, especially for global variables, which may be one reason why you should avoid using global variables. Yet another reason to avoid using global variables, because you can have some runtime overhead by having to go indirect through various kinds of global offset tables. And another issue that you have to deal with when you're using this pattern is the potential for overly narrow common interfaces. Some things work well with a common interface. Other things might require more configuration information than you might be able to pass through a common interface for all the different types of components. And you may end up trying to fit everything into a Procrustean bed where some things don't quite fit and you have to stretch them or reinterpret them in a more dynamic way. It turns out that these issues can be addressed by proper design of the generic interfaces, and we'll talk about this as we go further along in this particular module.